Welcome to the Horizon Interaction Patterns tutorial series. My name is Martin Schubert, and I'm a designer on the Horizon team focused on interaction systems and scripted mechanics. In this video, we will dive deep into the interaction pattern of pushing and look at ways you might want to use pushing interactions in your world to create fun and engaging gameplay. We will break down some approaches to using the creation and scripting tools to build great feeling pushing interactions. And we will look at specific pushing examples like punching bags and pushable buttons that are available for you on the asset library to import directly into your own worlds. These example assets are ready to use as is, or you can modify them to create totally new mechanics. In the physical world, grabbing is only one of the many ways we use our hands to interact with things. We also use our hands to poke, tap, flip, flick, slide, slap, and punch objects all the time. From hardware buttons on keyboards to touchscreens on our phones, we're constantly using direct physical contact between our hands and objects to interact with them. However, when we try to press a button in VR, there's nothing stopping our real-life hands from moving through the virtually solid object. So physical contact can only be simulated visually by our avatar hands being stopped, combined with audio and haptic feedback to reinforce the illusion. This kind of direct, physics-based hand-to-object interaction is unique to VR because it's only possible with the spatial inputs of tracked controllers. You don't need any instructions on how to push a virtual cube around with your virtual hands. Pushing objects is something we have lots of direct experience with. We know that pushing an object from its center will move it differently than pushing it from its edge. We know how to scoop things up and balance them against gravity, and we expect large objects to be heavier and take more effort to push than smaller ones. We've built up these expectations and intuitions over many years of honing our hand-eye coordination through the manipulation of physical objects. And, when designing VR interactions, we can tap into these skills directly. The new Physical Hands feature can make avatar hands physically collidable, enabling them to push physics objects directly. Physical hands are enabled by default in all newly created worlds. You can toggle physical hands on and off under Player Settings in the World tab. Note that there is no complexity cost benefit to disabling them. By default, a player's physical hands will collide with dynamic physics objects only, and will not collide with static objects like walls or tables. However, you can enable physical hand collision with static objects using a separate toggle under Player Settings in the World tab. This will enable people to rest their hands on solid, non-physics enabled objects. In addition to the world level toggle, there is a set physical hand collision code block, which allows creators to specify on a per player basis what objects a player's hands should and should not be able to collide with. You can also disable a player's physical hand collision entirely using this code block. Now that we know how to enable physical hands, how can we take advantage of this potential for interaction? What are some behaviors that make something satisfying to push? And how can you use pushing interactions in your worlds? Let's start with some general behaviors and then look at two example use cases, punchable targets and pushable interfaces. When you make an object physics enabled, it has default physics behavior and it has no collision audio. That means it's not especially heavy or slippery or bouncy, and when it collides with things, there is no audio feedback to tell you anything about the object's materiality or the collision speed. By adjusting an object's visual appearance, physics material, and physics audio material, we can make objects which feel more like they're actually made of specific materials. For example, by coloring a cube light blue with a fractured texture, setting its physics material to ice, and its physics audio material to ceramic, we can create something that looks like ice, slides like ice when pushed, and sounds like ice when hitting another object. Pushing objects with normal gravity strength makes for realistic behavior, but some of the most fun interactions come from lowering or removing gravity entirely. Whether you want to simulate being on the moon, underwater, or floating in outer space, pushing objects with non-Earth gravity can create unique gameplay. You can adjust an object's gravity strength on the object's property panel. If you find that objects keep getting away from you when you push them, especially if they have low friction or zero gravity enabled, then springs are a great way to bring them back. You can create a script and, in an updating event, use the spring push and spring spin code blocks, setting a target position and target rotation for the object to try to push and spin towards. You'll also want to set the script to local mode and make sure you transfer ownership of the object to whoever is interacting with it. By increasing the spring stiffness, you can increase the strength of the object as it tries to push or spin back towards its target position or rotation. And by decreasing the spring damping, you can make an object take longer to settle into its target position or rotation after being pushed. The push at position with mass code block enables you to apply a force at a specific position on an object. This is different from the push code block, which applies a velocity, and the push with mass code block, which applies a force, because both of these code blocks are applied at an object's center. Applying a force at a specific position on an object enables you to simulate forces much more accurately. For example, you could apply force at the position of a projectile's point of contact on a large object. Another interesting use case might be approximating the effect of buoyancy and what it feels to push an object around that is floating in a liquid. If we simplify an object to just its bounding box, we can check if each corner of the box is above or below the waterline. Then, if a corner is below, we can apply an upward force at the corner, proportional to how far below the water it is. We can do this in Horizon by putting a trigger at each of the 8 corners of the object, then writing a script to check each trigger's Y position every frame and comparing it to the waterline Y value. Then we can apply an upward force at each corner using the push at position with mass code block, scaling the force's magnitude based on how far below the waterline each corner is to roughly approximate a buoyancy behavior. We've looked at a variety of ways to create interesting pushing interactions, like playing with object materiality, zero gravity, springs, and buoyancy. Now let's get more specific and take a look at how you might make some different kinds of boxing equipment that behave somewhat realistically and are fun to punch. Using your hands to try to hit something with precision, power, and speed is a specific type of hand-to-object contact that has whole traditions and professional sports built around it. Unfortunately, in VR today, we really can't provide the haptic feedback appropriate to the feeling of hitting a heavy punching bag. The best we can do is use physics simulation to try to give the bag a sense of weight and momentum that provides some resistance to the hands, as well as adding audio, visual, and haptic feedback. We can also vary how the bag is being constrained to give it different behaviors when hit. Let's look at 3 examples. To approximate how a real punching bag behaves, we can look at the forces involved. We have gravity pulling the bag downward, and we also have the rope resisting that force pulling the bag towards its anchor point on the ceiling. To simulate this, we can create a bag by grouping a cylinder and 2 spheres together with a trigger at the top to use as the reference point where the rope will attach. Then we can write a script which will check the distance between the top of the bag and the other end of the rope attached to the ceiling. If the distance is less than the length of the rope isn't taut and we won't apply a force. However, if the distance is greater than the length of the rope, we apply a force to the bag in the direction of the rope's anchor point on the ceiling. In addition to the translational force the rope applies to the bag, there is also an angular force which keeps the bag upright. We can approximate this by using the spring spin code block and using the upright rotation as the target orientation. Then, to visually create a rope connecting the anchor point and the top of the bag, we can move a cylinder to the midpoint of both, rotate it to look towards the top of the bag, and scale its length to match the current distance between both points. Now that we have the bag behaving realistically, we might want to make it more satisfying to actually punch. If you set the object to look for collision with players in its property panel, then you will get when player collides with object events firing whenever your avatar's hands collide with that object. Using the new collision event code blocks, which contain data about the hit point, hit normal, and relative hit velocity, we can set up more precise visual, audio, and haptic feedback. For example, we can check the hit velocity, and if it's above a minimum threshold, move a hit VFX to the hit point and play it. We can also use the set volume and set pitch code blocks to let the magnitude of the relative hit velocity drive the volume and pitch of collision sound effects. Similarly, we can set various levels of haptic feedback to play based on how fast you punch the bag. Let's look at another example, a double-ended speed bag. A double-end bag is even simpler to simulate than a punching bag. Since this kind of bag is suspended by two elastic ropes, it has rope forces pulling it both upward and downward. We can simplify this by setting the bag's gravity to 0 and using the spring push code block to try to keep the bag at the midpoint of both ropes. Similar to the punching bag, we'll also use the spring spin code block to keep the bag upright. And to create a second visual rope, we can just duplicate what we did for the existing rope. A reflex bag is attached to the ground by a flexible pole, which allows the bag to pivot downwards in an arc when punched, then spring back up. There are multiple ways you could approximate this behavior in Horizon, but for now we can create a simplified version using just a spring and reverse gravity. By setting the bag's gravity to be positive 9.81, meaning it's being accelerated upward instead of downward, and using the spring push action every frame with a target position at the bottom of the pole, we can create a kind of tethered balloon which behaves somewhat like a reflex bag. Punching stuff is fun, but one of the most versatile ways to use physical hands is through pushable interfaces. Buttons and other pushable interfaces are everywhere in the physical world, from calling an elevator to spinning a big wheel or buzzing in to answer a question on a game show. In Horizon, you can use interfaces for all kinds of things. For example, to control music or lights in a social space, to control access to a secret area or objects as part of a puzzle mechanic, or to control a machine or appliance, just to name a few. Creators usually build animated buttons by using a trigger set to detect players and hooking it up to a script which animates the button to create the illusion of someone using their avatar hand to physically press the button. However, with physical hands, you can actually use the collision between your avatar hands and a physics-simulated depressible button to create the interaction. Combining this physics simulation with visual, audio, and haptic feedback will allow you to create interfaces that feel satisfying to push. To create a button, first you'll want to constrain a physics-enabled cube so that it can only travel along one axis in space, the direction we want to be able to press the button. You can do this by creating a collidable housing out of 4 white cubes with just enough space in the middle for the red button cube. Disable gravity on the button cube and also set its physics material to super ice, which removes any effective friction as it slides against the housing. Now if you use your hand to push the button, it will slide through the housing, which is keeping it physically constrained. Next, you'll want the button to spring back when pushed instead of just flying away. You can do this by creating a script for the button, where every frame you use the spring push code block to keep the cube at a position defined by a trigger gizmo. By adjusting the spring's stiffness and damping, you can tune the behavior so when the button is pressed, it resists being pushed, and when we stop pushing it, it springs back quickly. This works pretty well to create a springy button. Now we'll add a collidable cube at the bottom of the button's travel distance to physically stop the button. We'll also add a trigger here to detect the button and register that it has entered a pressed state. You can put a script on this trigger and let it handle the pressed state feedback, for example, making the button change color or playing a sound effect. Also, the trigger can relay information to an output object, like a text display. In this case, the button is hooked up to a counting number display script, which increments the number on every press. This button works well if you interact with it nicely, but if you knock the button sideways or upward from underneath, it's easy to push the button out of its housing. To address this, we can add 2 checks into our script. One to see if the button has moved out of place, and another to see if it's rotated out of place. In the first check, we can use a dot product operator to compare the direction between the start trigger and the button with the direction from the start trigger to the depressed trigger. If the button has gotten out of the housing, the dot product between these 2 directions will go from 1, where both vectors are aligned, to something below 0.99. Similarly, we can compare the button's current forward direction with the forward direction of the start trigger to determine if the button has rotated out of its housing. If we detect that either of these things has happened, we zero the button's velocity, disable its colliders, move and rotate it back to the reference trigger's position and rotation, and then re-enable its colliders. These checks and reset behavior ensure the button will always be inside its housing, and that it can only be pushed in the intended direction. Once we have a working button, creating a toggle, an interface that has an unengaged and an engaged state, takes just a few more steps. Let's put another trigger at the location we want the button to be when it's in its depressed state. The button will start with the top trigger as the target position for its spring. Then, when the button is pushed and has entered the detection trigger at the bottom of the travel space, we'll change the spring target to be the trigger we placed at the depressed position. This position should keep the button slightly above the detection trigger, so once the button is no longer being pushed, it springs back up out of the trigger and is ready to be pushed again to enter the detection trigger. Buttons can be used for controlling whatever you like. Often they're used in groups, like directional arrows, or on a keypad, which lets a user input a string of numbers. To create a keypad, you'll need to assign each button a payload string variable. In this case, the numbers 1 to 9. Then you'll need to write a script which will receive those payloads and display them on a text object with proper formatting. This keypad display script will also need to know the maximum number of digits which can be displayed, so that it can loop back around when the limit is exceeded. You could then use this keypad to gate the opening of a safe door or a passageway to a secret area by adding a line to check for a specific string of numbers, and then triggering the opening when the correct password is entered. To create a static slider which stays where we set it instead of trying to return to one side, we can simply set the target position of the spring to be the slider's current position. This means the slider will try to stay where you leave it until you push it again, and it makes all the possible positions along the travel axis valid input positions. To create a slider which outputs a value from 0 to 100, we can measure the distance between the start and depressed reference triggers, divide it by 100, and then compare that to the distance between the actual slider position and the start trigger to determine the current percentage output. Like the sliders, paddles are another example of using the same underlying button and toggle scripts, but modifying the shape and form of the interactive component to create a different kind of pushing interaction. By making a large paddle, you invite bigger, faster motions, and with a follow-through rather than a poke and retract action, like on a button. To create a free spinning wheel interface, you'll want to constrain the wheel's position so it doesn't move. Also, you'll want to constrain its rotation so it doesn't spin on any axis except the axis you want. To do this, create a wheel with spoke-like handles using a bunch of cubes to give accurate box collision volumes. Then enable physics on the group and also disable gravity. If you spin the wheel now, it will just tumble and float away. However, you can add a script to the wheel, which every frame uses the spring push code block with very high stiffness and damping values to keep the wheel held in place. Then, to constrain the wheel's rotation, every frame you can get and store its angular velocity, then use the stop physical motion code block to zero out the wheel's linear and angular velocities, and finally, reapply the original angular velocity, but only along the world X, Y, or Z axis, whichever the wheel is pointed towards. To use this wheel as an input, you can break up the wheel's rotation into distinct sections, then compare the wheel's current upward direction to the original upward direction, thereby determining when to increment or decrement the output. By splitting the dot product of these two directions into small ranges, you can capture fast spinning movements. And to complete the interface, you can hook up a text display and add a tick marker that changes color and plays a sound with pitch and volume driven by the magnitude of the angular velocity. Lastly, to create a wheel which rights itself when not being pushed, you can add a spring spin code block to the script. By using the original orientation as the target rotation, you can tune the stiffness and damping values to get the wheel to resist being pushed and to spin back to neutral when no longer being touched. By putting a block beneath the wheel and extending the topmost spoke, you can physically limit how far the wheel can be spun in either direction. For example, limiting the output from -5 to +5. We hope you found this tutorial module on the interaction pattern of pushing useful. Please visit the pushing examples world to try pushing, punching, and spinning these examples for yourself. Like most things in Horizon, pushing stuff is a lot more fun with other people, so grab a friend. You can also find all of the punching targets and pushable interfaces shown here in the asset library, ready to be dragged and dropped into your own worlds and used in your gameplay. Going into build mode and tinkering with the examples is a great way to understand the new features. Regardless of what you do, have fun and keep learning.